Hey guys, and welcome to Unit 3. In this unit, we're going to be taking a look at linear functions. Now, a linear function is simply the graph of a line, something that has a constant rate of change. So today, we're specifically taking a look at the graph of the line y equals mx plus b. That is also known as the slope-intercept form of the equation of a line. So let's jump into today's notes with a little bit of terminology. We're going to start off by talking about y-intercepts. That's simply the y value, or the point where the line crosses the y-axis. So up here in the top right-hand corner, you can see this linear function comes through and it has a y-intercept here of 2. Note that this is also where x is equal to 0. So when x equals 0, that's where you'll find your y-intercept. A linear function, simply a line, and it has a constant rate of change. Now remember, that rate of change is known as the slope. So this is called the slope-intercept form of the equation of a line. And it goes like this: y equals mx plus b. Now, there's a lot of letters there, but those letters represent numbers. Y and x are always a part of that equation, but m is going to represent the slope, and b is the y-intercept. Remember, the slope is simply the change in the y over the change in the x. Another way of saying that is y2 minus y1 divided by x2 minus x1. Another way that we state that is the rise over the run, and that's nice and easy to count when we have the graph of a linear function on the coordinate plane. Next up, we have the x-intercept. That's the point where that line crosses the x-axis. Now, you'll also note that this is where y is equal to 0. So up here in our graph, we can see that our x-intercept here is where x is equal to 1. Finally, let's talk about the slopes of parallel lines. You guys learned last year in geometry that parallel lines have the same slope. They'll never intersect. All right, jumping into today's examples. We're going to start off by talking about writing a word problem in a linear, into a linear sentence or a linear equation here. A pool contains 85 gallons of water. Suppose that a hose adds water to the pool at a rate of 7 gallons per minute. We want to write an equation for a linear function that represents the amount of water in the pool t minutes after the hose is turned on. So let's start off by identifying our variables. First of all, we have t, and that represents the number of minutes our water is running. All right. Now this is going to be our independent variable. Our dependent variable is the amount of water, and we're going to call that our variable a. And that's going to represent the amount of water that's in the pool. So we'll say H2O in the pool. All right, so simply writing the equation here might look like this. Our amount in that pool is going to be equal to our beginning amount, which we already have 85 gallons in there, plus the number of gallons that we're adding per minute, which would be 7 times t, the number of minutes that hose is running for. So here's our linear function. 85 is going to represent our y-intercept, and 7 is going to represent our slope. So if we were thinking of this in terms of y equals mx plus b, we could rearrange these two around, and we'd have a is equal to 7t plus 85. All right, example 2. Now we're going to add to that a nice little picture of our linear function. Stu has $204 saved in his bank account. Every month he withdraws $20 to pay his cell phone bill. How much money will Stu have remaining in his account after m months? So let's start off by defining our variables and writing a linear equation. So again, we're going to let a be the amount, and this time it's going to be the amount of money in his account, and m is going to be the number of months into paying his cell phone bill. All right, so m is going to be our independent variable, and our amount here of money is going to depend on the months. All right, writing our equation then, we're going to say the amount he has is going to be equal to the original or starting amount minus $20 for every month he pays his cell phone bill. So if we were to write this in slope-intercept form, this might look like y equals negative 20 m plus 240, where 240 is our y-intercept and negative 20 is our slope. All right, now it says to give a classy graph. Now a classy graph means that we're going to label our axes we are going to neatly plot some points. Typically it's 2 to 3 points where we can see their coordinates, and we're going to draw a nice line or curve depending on what our graph calls for. So along the x-axis here we have our number of months. We're going to quickly label these. And then here we have our amount in our account. So we're going to go up by, let's go up by 40s here. All right, at 0 months, we know that he has $240, and every 2 months, he's going to be paying off $40 here. So we're going to go down. Here it's at 2 over and 200. At 4 over, he's going to be down to 160. At 6 months, he's going to be down to 120, so on and so forth. All right, so here is a classy graph. Now I'm just going to connect all of these points here with a line of as best I can, and there we go. Our final question says, how long will it take before he runs out of money? So in other words, how many months? So this would be an issue of substituting 0 in for the amount now and working backwards through our equation in order to solve for m, the number of months here. So we're going to subtract over our 240. That gives us negative 240 is equal to negative 20m. Divide over by that negative 20, and m is going to equal 12. Now we could continue our pattern out onto our graph here, and we would find that same answer here. When we reach 12 months, we'll be at $0 left in that account. All right, example 3. Here we're going to do another example like this here. We have an online t-shirt printing company that charges $35 for the artwork and setup fee, plus an additional $4 per printed t-shirt. So we're going to say that T is going to represent the number of t-shirts, and that's going to be our independent variable. And then the amount, or the cost, actually let's go with C this time, is going to be our total cost of printing all of those shirts. So coming up with an equation here that models this situation, our cost would be the $35 up front plus $4 each additional t-shirt. So if we were to write this in slope-intercept form, we would see that C is going to be equal to 4t plus 35, where our y-intercept is 35 and our slope is 4. Again, we're going to give a classy graph and answer the question, how many t-shirts could be purchased with $165? All right, so we're going to label our axes. Okay, once we have our axes graphed here, then we want to plot a couple of nice points here. So if I buy 1 t-shirt, that'll be that $35 plus 4 additional. That will give me pretty close to $40 here. And then let's go out to do 10 t-shirts. 10 t-shirts times that 4 would be $40 plus the additional 35. That's going to put me somewhere right around that $75 mark. So we're going to come out here and plot these 2 points. All right, once we have those 2 points on there, it only takes 2 points to construct that line, so we're going to draw that line through those 2 points, and there you go. The remaining points would lie on that same line there. Finally, we're going to answer the question, how many t-shirts can we purchase for $165? So we're going to plug in $165 for our cost and solve for T. All right, we're going to start by subtracting over that 35. That gives us 130 is equal to 4t. Divide off that 4. That's going to go in there. 32 with a little bit of a remainder there, 32.5. So my question for you is, can we really buy half a t-shirt? No, we're going to have to round that down to just 32 t-shirts. All right, in our final example for today, we have a line that contains 2 points, A and B, and another line that contains these 2 points, C and D. The question is, are these lines parallel? And really what we're after is, are their slopes equal to each other? That's the big question. So let's start off by finding the slope of AB. The slope of AB can be found by taking a difference in the y's and dividing by a difference in the x's. All right, that gives us negative 12 over negative 4, and that slope reduces to 3. Next up, we're going to find a slope of CD by taking the difference in the y's and dividing by a difference in the x's. All right, and again, that's going to give us 6 over 2, which is also 3. So because these have the same slope, these two lines are going to be parallel lines.